Welcome back to another episode of Game Theory. We just finished talking about games with a finite number of repetitions. Now move on to look at infinite repetitions. So first we have to develop a tool that might be new to you guys, though perhaps you've seen it in one of your earlier econ classes. The idea begins with people discounting the future. All else equal, you'd rather have stuff now than have the same thing later. So you think about it in terms of receiving cash, but it's true for things beyond that. So if there are no inflation, you'd still rather have money now rather than get paid a year from now. And there is a logical reason for that. If you get paid right away, you can start saving that money and earning the interest rate on it. If you get paid in the future, then you gotta wait before you invest, which means you can't accumulate as much interest. So $100 today and $100 a year from now, even with no inflation, are not the same thing. So you actually calculate the value of money today and the value of money in the future and see what the conversion rate is between them. Let's have little r be the interest rate. So if you take your $100 today, put it in the bank right away and start getting interest, what you'll have a year from now is 1 plus r times 100. And you can look at further time periods than that. With the same kind of reasoning, you can figure out what $100 today would be worth in 2 years. So now if you do that for 1 year, you get 100 times 1 plus r. If you put it in the bank, if you keep it in the bank for another year, you get 1 plus r interest again. So now you're getting 1 plus r squared. So you're getting compound interest. So how much is $100 today worth in 3 years? perhaps you're seeing the pattern by now. So in 1 year, I got 1 plus r. 2 years, 1 plus r squared. So it seemed natural that in 3 years, I get 1 plus r cubed. So I got 1 plus r squared interest in 2 years. If I get another year of interest, that'll be another 1 plus r times 1 plus r squared. That comes out to 1 plus r cubed. So now I can look at things from an inverted perspective. Instead of asking how much is $100 today worth in the future, we can ask how much is $100 in the future worth in today's dollars. It just involves rearranging these equations. So for our first equation up here, I can just divide both sides by 1 plus r, and what I'm going to get is 100 over 1 plus r today equals 100 next year. Likewise, $100 in 2 years, to find that, I got to divide both sides of this equation by 1 plus r squared. Very last one, how much is $100 in 3 years worth to us today? Go to this equation, divide both sides by 1 plus r cubed, and you get your answer. So $100 over 1 plus r cubed is, should specify, today is $100 in 3 years. So that's how you can make the conversion. So this brings us to the concept of present value. Other terms for it, some books will call it net present value, and I'll use NPV for that, but it's the same idea. So you're making some payment or you're receiving a payment sometime in the future, and you're converting that into today's dollars. That's what the present value is. Now my analysis over here was all based on there being no inflation. So if you worry about if I add inflation to our story, does that change things? Well, I demonstrate in one of my other classes, Econ 445 Public, I demonstrate that inflation actually does not affect the present value calculations. It turns out inflation affects both the nominal value of the money, but also nominal interest rate symmetrically, so this cancels out. So if you would take that class, you'll see a proof of that result. So basically, I'm saying don't worry about inflation when you're using present value. So for notation, let's say that pi 0 is going to be your payoff today. pi 1 is going to be your payoff next period, the next repetition. And pi 2 is going to be your payoff 2 periods from now. Etc. Then in math, here's the big formula for present value. And this is an important result. So the present value of all your payoffs is going to be pi 0, your payoff today. Now, your payoff today is already in today's dollars, so there's no conversion necessary. For next period, pi 1, that's received 1 period from now, so we got to discount it by 1 plus r. We said that 100 next year is only worth 100 over 1 plus r today. You have pi 2, 2 periods in the future. To convert that into today's dollars, you got to divide by a 1 plus r squared. Then you get pi 3 later on. Discount that by 1 plus r cubed. And so on. So before I could go into the infinite future, so I'd be wondering how to actually compute that in practice. Well, with infinitely repeated games, what often ends up happening is that the players start going for the same strategy over and over and over again, and there's a handy shortcut when there's repetition. So first of all, something about notation. I motivate our story in terms of interest rates, but it's often more convenient to use delta equals 1 over 1 plus r to make our formula more compact. So that gives you present value is going to be pi 0 plus delta pi 1, because delta is 1 over 1 plus r, so it's just delta pi 1 here. Here you got 1 over 1 plus r squared, so that's going to become a delta squared. 1 over 1 plus r cubed is going to be a delta cubed. Etc. So you can see that writing delta instead of 1 over 1 plus r is a little bit easier. So, potential objection. A game can't actually go on forever. So why are we talking about infinitely repeated games? Well, infinitely repeated games they end up being identical to a more realistic scenario that can actually occur in real life. So what if the game continues with probability delta and the game ends with probability 1 minus delta? So the probability of the game continuing twice would be delta squared. Probability the game continues 3 times in a row would be delta cubed, etc. So the present value of an infinitely repeated game is going to be the same as the expected value of a game that continues with probability delta ends with probability 1 minus delta. So it's probably easier to think of the game as not actually being played an infinite number of times. Rather, you can think of it as being played continually with probability delta and ending with probability 1 minus delta with every single repetition. So this is not unrealistic. So I mentioned briefly that trying to compute this in practice could take you an infinite amount of time, but as a shortcut, the players end up doing the same thing over and over and over again. And in equilibrium, they will be doing the same thing over and over and over again. So the shortcut we'll see in a moment is going to apply. So the shortcut is that 1 plus delta squared plus delta cubed and so on equals 1 over 1 minus delta if absolute value of delta is less than 1. So the payout to get these periods is the same every time. So if pi 0 is the same as pi 1, same as pi 2, etc., you can factor all the pi's, you get this, then you use our shortcut over here, and that gives you a very handy calculation of the result.